right into what we want to cover. What we're going to cover today is going to be on the test. There will be questions on it and what we covered last week. We will have a little bit of parallel flux on the test as well, but no coding this time on the test. I'm going to give you guys 90 minutes for the test. And right now there's 20 questions, but that's going to be pared down to about 15 questions is what I'm aiming for. Okay, so if you see more than that, too bad, sorry. But that's where I'm aiming, between 15 and 20. I'd like to go fewer, but okay, let's take a look at some microservice arc. Some of this is going to be a little bit of a review at the beginning, but there's a purpose for that. I want you guys to make sure that you have really strong in your psyches, in your heads, not the Java stuff as much as the concepts of microservice scalable architectures. Because in reality, when you're out there in the field and working, you're going to see lots of different languages. So I want you guys to be able to identify the patterns that are in there and to make sure that they're used appropriately. So let me hit the beautiful share button. Did I already hit it? No, I did not. All right. Hit the share button and let me bring up. Yeah, here we go. All right. Sorry for the sliding. All right, so let's dive into this. So one of the key things we want to make sure, key concepts of computer science in general, is loose coupling, and microservice architectures provides that in a very good way, right? We can do loose coupling, and cohesion is the other key aspect in almost any language that we do. But microservices can really kind of enforce that by having boundaries around the module or the microservice that I'm doing. If I have that microservice sitting there, then by itself, it can run independent. By itself, it is pretty loosely coupled with the other microservices, right? Now, that is at program time and compile time, loosely coupled. I need to make sure that I continue that coupling as loose as I can by not having implicit coupling between microservices. Now, what do I mean by implicit coupling? What do you guys think? What does Dr. Postper mean by implicit coupling?
So wouldn't that be like updating a DB and depending on that value? So
Yes.
It's stuff that basically is dependent, but you're just not expecting it.
Yeah, it's dependent, but it's not coded anywhere. Right? So it just happens, right? It may be a value I'm dependent on another microservice. That dependency that I have on that value being a very specific value is a coupling, right? And a lot of times these implicit couplings are very, very difficult to find. I would rather have an explicit coupling than an implicit one, because explicit means I said, include this, or maybe it's even in the documentation. This is required. I would rather have that than an implicit one where I can't really pin it down. They're hard to debug and they're very hard to find later on, and they can cause these massive cascading failures. I've mentioned in class before, one of the biggest ones happened in 2022 with Amazon and their CloudWatch. CloudWatch is their tool that they use to watch all the microservices. And those microservices, it says whether those microservices are up or down. And they used a pooling technique instead of event-driven. And what happened was CloudWatch went down and the reporting service was separate, and the reporting service showed everything green. But because CloudWatch was down, nothing could reconnect, and everything showed green. Massive cascading failures everywhere. It brought down Amazon on the East Coast for about 18 hours a day after Thanksgiving, the biggest shopping day of the year, right? Massive failures, billions of dollars were lost. If you are interested in hearing more about, I broke down the analysis of what happened on one of my podcasts. I'll send that off to you guys. It's an interesting listen as I go through the log files, because they released the log files. You can go through and see where the cascading failures happen. And the implicit coupling was there. Okay. So another thing that you need to look at is how big is your microservice going to be? Is it going to be a nano service, a microservice, a milliservice, or a service, or a a big kilo service, or a Terra service, whatever? The size really does matter, and there's some trade-offs when you start looking at microservices. You can go super fine grained where it's only doing one specific thing, and I can scale that one thing, very, very quickly, but it adds complexity. As the number of microservices goes up, I have to orchestrate those. And so now it becomes much more complex. I've seen some systems with several dozen, we're talking 100 or more microservice types, and it's very hard to keep track of what's going on. I've seen others that only had 2 microservices, but I couldn't scale how I needed to, right? I drug along a bunch of other code with it and other parts, endpoints in the REST interface that were now bogged down. So coming up where you divide your microservices is an art. It's not something that I can just say, you just do it this way every time. That's completely dependent on the application and its use and the number of users or number of endpoints that are using it, right? And other microservices that are using it. But you got to play around and adjust for those things. Keep both of these things in mind when you're doing it, okay? Another way of decomposing microservices is by business capabilities. Now, there was, back in the 1990s, there was a big push for object-oriented technologies, and there were a couple really interesting architectures that were developed at the time where every single object inside your system became independent and became basically a microservice. So every single object could be run as its own microservice, and all of its functions or methods were run in the same process space. Right, and that was a very interesting architecture. A lot of systems fell over when you had several 100,000, of these objects, and some systems have millions of objects. So it doesn't scale great that way. So other people started looking at different capabilities, so more function-based decomposition for microservices, like domain-driven design, where I'm saying I've got an order manager instead of just an order, right? I've got an order manager. They manage orders. I got a payment service. It manages payments. I've got a notification service that notifies the customer of changes to their order. So now you can see these are function type things. They do one type of function and the data flows through them. This is very common. We see this a lot. And it's easy, the boundaries are easy to determine in this case. So it works pretty well. And this is the one that we see most often. Okay. We also need to make sure that when we're designing our microservices, that we can scale them horizontally based off of the architecture. So if I have an order manager and I'm getting 10 orders an hour, I can probably handle that pretty easily with one microservice, one instance of it. But if I'm handling 10 million orders an hour, I need to be able to scale that horizontally so that I can take those orders in individually. I can maybe take one order at a time. So how many can I take? Maybe I need 1,000 of those running at the same time. And I need them to be very elastic, meaning that I can grow the number of instances of that microservice and shrink them so that I'm not always consuming resources that don't need to be consumed. So having that elasticity and load balancing between the same instances of the microservice is is horizontal scale. That's the concept of horizontal scale. Another thing, and I kind of argue a lot with this one, and that is if I make my microservice stateless, then they're a lot easier to scale, meaning that the microservice itself does not store any state itself, but that it is basically just this function that it gets data, processes it, sends the data off, and then can shut down, and there's nothing there. So this works really well for highly horizontally scaled applications. It also makes it somewhat easier to recover from fails, because if you've got 1,000 microservices or 10,000 instances of a microservice running, chances are you're going to get one or two of those that fail. So in order to recover from that, I can just fire up another one and run that same transaction through. For an order service, that works really well, right? So if you've got a long chain of services where information is passed from one to another, that works pretty well too. If it fails sometime, I can restart that service, try the transaction again. A lot of times, in order for us to keep the state not of the service but of the object I'm working on, we need to store those in service memory or in this transient memory that's accessible by everything. And Redis is one of those tools. It's a persistent key value store that's distributed. It works pretty well for this sort of thing, but there's lots of key value stores that are out there that you can use for the same thing. Redis is just an example of that. All right, there's a lot of different communication patterns, and we've talked about a lot of these, but we're going to go more in depth in these. There's two big buckets. There's synchronous communication and asynchronous communication. You guys need to be able to tell me what the difference is between the two. This is going to be very important. Okay. Synchronous means what? Anyone, speak up now. Synchronous means what?
One at a time.
Say that again, Ron.
One at a time.
One at a time. That's close. That's very close.
You send a message, you wait for it, and it blocks.
Correct. Right. So it's one at a time. I send a message and I wait for a response. Request, response. Yeah, you guys got it, right? So I'm waiting for that response to come back. That's synchronous. And it is true, it's one at a time, but I'm really making sure you guys understand that when I send something, I'm waiting for a response back. That's synchronous. Asynchronous is using messages. I send a message and I may get a response back. I may not. I don't care. I'm going to keep working. If I get a message back, then I'll handle it when I get it back. That's asynchronous, right? There are some cases, believe it or not, where all I'm going to do is send a one-way message and I don't care about a response at all. I'm just going to say, I'm here. That's the most common one, is a health ping. A lot of times these microservices will send out a ping saying, I'm alive. I'm alive. I'm alive. I don't know if anyone's listening, but I'm alive, right? I don't expect any return back, but if I'm alive, maybe someone will send me some work to do, right? That's a common one-way asynchronous message. Two-way asynchronous messages means I'm both the client and the server at the same time. This is very common in peer-to-peer networks, where I'm going to say, hey, I can do some work. And then someone sends me back some work to do. Right? Different than I'm alive, because I'm expecting something back. But I can go and do other work while I'm waiting for that other thing to happen. Okay. In the case of like an order system, like an order manager or order processor, it may be triggered to do something when an order is created for the first time. Oh, a customer creates an order, boom, all of a sudden an event is sent out and this service says, ooh, someone created an order, I'll grab it and do the work. That's kind of more of a message queue. The orthogonal to that would, if I'm doing synchronous communication, would be that the user interface says, go create this order. And there's a REST interface on the other end that says, create order, and then sends a response back with a order ID. That's asynchronous, or that's synchronous, compared to asynchronous was, I got an order create event. Okay. You guys understand the difference? Any questions?
Yeah, I think so. I like using analogies for like everything. So synchronous is like you order your food at a restaurant counter and then you just have to wait until your food's ready. And then asynchronous would be like you ordered it online and then you're going to have it delivered so you can step aside and do something else in the meantime.
Yep.
Okay.
Yep. Good. Yep. You order, you order it online, but you don't have to stop watching your movie at home. It shows up at your door, someone rings the doorbell and you get it. That's asynchronous. Good. All right. Fault tolerance and resilience. So we have used the circuit breaker pattern. Here are some, and the way we've used it is when we were doing the parallel task and we had the with the composable threads, composite threads, scoped composite threads. When we were doing that and we said, hey, I'm going to run all these things, but fail, if I get a failure, you'll quit. That is the whole concept of the circuit breaker. If I get one failure, stop all the other things that are going on. Right, that's a circuit breaker pattern. So you guys have actually used the circuit breaker pattern if you didn't know what it was. Okay, there are some microservices out there that handle that, and some libraries that handle that. And here's two of them as examples. The other thing are some best practices. When I am talking via microservices, I have to realize that I'm going over a network. Networks go up and go down, right? But how resilient you are depends on how you've coded those microservices. If I'm sending an event out, or if I'm doing asynchronous communications, where I'm opening up a socket, I'm sending a request via REST interface, and I'm waiting for a response back. If I get that service is down, what do I do with that failure? Do I retry? How often do I retry? If I retried 5 times and I said it's not working, what do I do then? I need to back off what's going on. I need some solutions there. So retries and timeouts, these are common things that you're going to see in microservice architectures. Make sure you're coding them in. If you don't, and you just send, oh, I just tried once and it failed, it's no good. That's a very fragile, very rigid type of architecture. It will fail often because comms channels go down. They just do, right? Especially if you're doing anything that is across a wide area network, which means outside of your data center. If I'm connecting to a REST service, like a large language model at OpenAI, it happens all the time, where I send a request out and it says, we're too busy right now. Well, what am I supposed to do with that? Right? I just fail miserably and then everything falls apart? Or do I try a different service? Or do I wait? I'll wait, 5 seconds and try again, whatever the case may be. That's that retry timeout concept. Okay. The other thing we really didn't talk a lot about, but it is a really critical thing that you need to make sure that you're handling, and that is security between these microservices. If you leave an open port with no authentication on a microservice, it will be attacked. It absolutely will be attacked. And a lot of people have taken the attitude, well, I'm behind a firewall, so it doesn't matter, right? Because someone's got to get through my firewall. Well, if they do get behind your firewall and you have got all these microservices that are not doing any kind of authentication, that means they get to run the gamut and they can get in and cause massive havoc all over the place. Do not think that just because you use a unique port number or unique IP address that someone's not going to find that. Obscurity and obfuscation is not security. That's just hide and seek, right? And especially some of the best hackers in the world come from the United States, obviously. The NSA has a great cybersecurity hacking team. Israel with Mossad, and Iran, North Korea, China, Estonia, and Russia. You guys want, if you want those people in your data, don't authenticate your microservices, because once they get through that firewall, they can run havoc over everything. Okay. All traffic should be encrypted as well using TLS, which is going to do encryption key sharing between your microservices. Good news is there are libraries that handle this all very well. And most of the modern languages already have this sort of stuff built in. You just have to make sure you're turning it on. Okay. Okay, another really important thing that we need in microservice architectures that we don't need as much as in monolithic is monitoring and logging. Because I've got all these microservices running in different places, they produce logs, but those logs are scattered, right? And if you've architected it by decoupling your microservice from physical hardware, your microservice can float around your data center all day long, right? It can even float outside of your data center in the cloud, out on the edge devices, wherever you want. If you've architected them appropriately, you kind of want that flexibility, right? So you need to come up with some kind of logging mechanism. There are lots of different options out there. The most common ones are something called an elk stack. It's actually 3 different tools stacked together. There's FluentD. There's a whole bunch of other ones out there that will even gather system logs off of individual systems and partition things out. As you can see, we're adding more complexity to our system, right? That's one of the problems with microservices is I have to create additional tools to monitor and orchestrate these, right? There's also distributed tracing, which we're going to see one of the design patterns that we're going to look at today called the Saga is actually going to use Jaeger to actually do distributed tracing. So I can see individual loads on individual microservices, and I can take those loads and determine where I'm going to send new events, or if I need to spin up new instances of those microservices. So these are some concepts that you guys should be aware of. Okay. The other thing is, it's great to code all this stuff. It's another thing to code it in large groups and deploy it and test it and things like that. Because I'm not dealing with just one application, a big monolithic application anymore, I'm dealing with several dozen small applications that can be versioned independent of each other, that get deployed differently and independent of each other. I need to automate some more. How you're going to build and deploy these services in different environments, both in development, which means maybe on your laptop, in a development server where you're collaborating with other developers, in a test environment, and production environments. Meaning, I may have more than one production target for this sort of stuff. You need to make sure that you've automated that as much as you possibly can. If not, then all you've done is you've shifted a lot of the complexity into deployment. And that's where there's so much variability. A lot of things can go wrong there. So it's best to automate that if you can. Okay. There are different deployment strategies. One is, there's a couple out there. These are the most popular. Blue-green says that I've got 2 instances of production running, a blue team and a green team, and only one is fully production at a time. I'll deploy the green team. I'll run a bunch of tests in production, and then I can flip a switch and it'll flip over to green. That's a blue-green deployment. It minimizes downtime dramatically. And a lot of times the end users won't even know that you've done an upgrade. Then there's a canary release. This one, I'm going to send, maybe part of my production is running the new microservices, and I'll see if it fails. If it fails, then I can roll back to the other instance. And then there's a third one I didn't mention, and that is just release and pray. A bad option, right? Don't do that. Don't do the I'm going to burn down the other one and just deploy it and hope that it works. That does not work. I have done that myself more than once, and it's always come back to bite me every single time. Okay, any questions on these 8 concepts of microservices? Does this all make sense? Ask now or forever hold your peace. All right, let's keep going. Common patterns and practices. So let's go over some of these. We've already talked about monolithic versus microservices and the trade-offs between the two. You guys should be able to articulate that, right? Monolithic, harder to scale because I have to scale the whole thing, right? They tend to be easier to debug because I have all the code in one place. I can easily walk through with the debugger as I'm going through it, but they're more cumbersome. If I have only a section of the code that needs to change, then I have to release the whole thing. They tend to increase coupling because there are no boundaries between modules that are easily separatable. And we see this when people are coding, oh, there's a nice function over there, I'll just use it. Instead of looking at the whole architecture, right? Microservices, the benefits of microservices, you guys should know: scalability, low coupling, high cohesion, right? Releasability. Go back and look at some of the old notes on the monolithic and microservice architectures. Okay. We talked last week about 2-tier, 3-tier, 4-tier, and N-tier systems. But if you break them all down, they really come into these 3 different layers: a presentation layer, a service layer, and a data layer. Even in the service layer, I'm going to find several different layers inside the service layer and also in the presentation layer. Right. And that's where you get the 5 and 6 layered concepts that are out there. Remember, this all has to do with your application space and how fine-grained you're going to make your microservices. There is an interesting thing I'm starting to see more of, and that's in the database or in the data layer, where I've got a database per service concept. Instead of sharing common databases, it increases cohesion dramatically and decreases coupling. When I say, like, the order manager, for example, has a database that just has orders in it. It doesn't have any payment information. It just has orders. And then the payment service has a payment database. No order information, just payment information. It may have an order ID, and that's it, but nothing else. They just have a reference to an order ID. So we're starting to see these happen more and more, and there are some benefits to it. Portability is one, scalability is another, and decoupling is a third. So look for those when you guys are out there in the real world. Okay. Event-driven architectures. We're going to go over this quite a bit today on some of them. There's event streaming, where I'm just sending events, and there's a pub-sub model that a lot of these event streaming technologies can handle that we're going to talk about. And then there's also just event peer-to-peer type networks that fit in that event-driven architecture. Example on when to use events goes back to, let's talk about this order system. Instead of the interface saying the customer is creating an order, call the create order REST interface. Instead, it says an order was placed event. And in that event, it may contain a bunch of information, but now it's just an event that happens. And now the order service is looking for those types of events. It finds it and can do it. The client is no longer blocked. right? Where the other one with synchronous, it's blocked waiting for an order ID. Okay. Let me show you a couple diagrams that show this working. The database per service architecture, I've already talked about some of the benefits, the decoupling of the database and its access. I can actually also do something we're seeing a lot more of as well, where database access is only granted to services that have been authenticated with that database. So instead of having user data access, I have service access and authentication. So instead of having all these weird accounts in your databases, like, oh, here's my admin account, here's a service, you set it up so that the service is the user of that database, and only the service and instances of it can talk to it. This really locks down the database and improves security. So that's another interesting benefit to this. One of the downsides to this is if I'm scaling too much, I may have to have multiple replicas of this database, which increases complexity, and it could cause eventual inconsistency in the data, right? But that's a normal problem that I have even with a centralized database if I have replicas of it. But with this database as a service concept, if I'm having references between databases, this could be a problem. So just, watch out for it. But, here's a great example. I can have an order service that uses MySQL. I can have an inventory service that's using MongoDB, and I can have a payment service that uses Postgres. So depending on the type of data it is, I may choose a different data store, database based on that. So that gives me that flexibility. Okay. Deployment options. The two big deployment options outside of the Spring Boot world are basically Docker and Kubernetes, right? Docker, I really enjoy Docker for development because it's easy. It was written to be easy. It's a one-click deployment type of thing. Kubernetes was developed by Google and pushed into the open source community, and it acts like open source. You need to stand on your head. You need to read, thousands of pages of documentation to get this thing stood up, but it's highly flexible and configurable. And there's been lots of offshoots to try and contain it into a one-click concept. It's great for production systems because it's highly configurable for your different configurations that you want. But for running just on your desktop, Docker for me is an easier way to go. And Docker's even created a Kubernetes orchestrator in their Docker desktop, which is a one-click option as well. So these tools here handle deployment, scaling, and most importantly, probably one of the hardest things with microservices is networking. Both of them use the concept of overlay networks. Overlay networks create these virtual networks that can span multiple networks and create this virtual network across them, so that, and I can have thousands and thousands of nodes on these virtual networks, and they all look like they're on the same network, so the communication happens much easier, and you don't have to worry about routing or any of that stuff. It's all handled for you, so it makes your life a lot easier. Right. Okay. Okay, let's talk about something you guys already have done. We've done an API gateway design. You guys used Eureka when we did in assignment 2. Whether you remember this or not, you did. And remember, API gateways have a lot of them built into them, the service discovery. So when I create my service, I register to these API gateways. I tell them what I can handle. And now all the clients come directly into the gateway, and the gateway is directing traffic, right? Now, there's one cool thing about API gateways. It can be your central place to do your authentication. When a user comes in from the outside, I can authenticate them right then and there. And then from then on, I can pass that authentication token to all the microservices. So all my authentication is done in one spot. It's a great place to do logging and monitoring, and because that's where all my traffic is coming in. One of the downsides to API gateways is I have a bottleneck now because everything has to come through one. So we start seeing API gateways that are federated that can scale very easily horizontally and can handle different types of loads. The other benefit of an API gateway, of course, is I can throttle. If I'm getting a DDoS attack, a distributed denial of service attack, people could attack my gateway, and I can throttle those requests and even shut down nodes without disturbing the back-end microservices. So your API gateway is kind of that guy with the bulletproof vest standing in front with everyone behind it. Okay. There's lots of different tools out there. I just grabbed a couple ones that we see inside the Spring Boot. We've been using Eureka is the one that we've been using. Okay. Serverless microarchitectures is another one. You guys have probably all heard of Lambda, AWS Lambda, Azure Functions, FAS, Function as a Service. That's what we mean when we talk about serverless microservices. These are, I would call these more like nano services because they do one function. And it's typically a small amount of code, less than 100 lines of code, sometimes even like 20 lines of code. Data comes in, data goes out. I transform the data, I do something with it, right? And I'm only enacting these functions on demand. So the dirty little secret on the back end of this is I've got a whole bunch of threads that are running in different processes that are sitting there waiting for someone to tell me which function to run. Oh, I run this function with this data. I fire it up. I shut it down. I fire it up. I shut it down. They're very powerful tools if you have that type of work that you're doing where I'm just transforming data and it's massively parallel because I can fire up hundreds of thousands, millions of these Lambda functions or these functions as a service. If you're using AWS Lambda or Azure Functions, you are now tied to that platform. Let me reiterate that. You are now tied to that platform. That means if you don't like the cost structure of AWS Lambda, too bad. You have already gone hook, line, and sinker into Lambda. So if you are going to use these, use abstraction layers if you can, so you can either host your own if cost is a concern, or you can play Azure against AWS if you're with a big company and you've got a lot of purchasing power. You can play them against each other to get better cost structures. Right? We, as computer scientists, I hate to say it, we can't just live in the world of infinite resources and money because the reality is that doesn't happen. Okay. Function as a service, these serverless microservices, they are stateless. You can't store state in them because they disappear. You start them up, they do something, and they're gone when they're done. They get blown away, right? So keep that in mind. Also, they're highly portable if you put the abstraction layer in. Okay. All right, let's take a look at one of these advanced example. It's the basic setup of an API gateway with services, right? You're going to see the API gateway and what it does here. So let's take a look. So I've got my API gateway, my user there on the bottom. My user requests something. It gets forwarded from the API gateway to the order service. The order service may walk through these steps. It's going to call a REST or a gRPC. gRPC that's Google's remote procedure call. It's another protocol like REST, but it's actually much faster and much more type safe. You guys should at least look at that one of these days. It's a very interesting protocol, right? In this case here, though, I'm doing what kind of communication between these microservices? Can you tell just by looking? Asynchronous or synchronous?
Synchronous because of the REST call.
Yeah, you got it, Hamza. Yeah, it's synchronous, right? Because request, response, request. And if you look, all the requests, the order service requests, do I have inventory? can I now go to payment, right? The coordinate payment, it's asking for inventory, then it's asking for payment. And then, oh, it gets the responses back, both the inventory update and the payment response, they both come back. And now I send a response back to the API gateway, all the way back to the user. So it's very synchronous. Okay. Okay, let's look at an event-driven example with the same architecture or the same microservices. Okay, let's take a look at this one. Okay, a user comes in and creates a order service, right? It says create order. That event gets published onto an event broker, which is my pub sub hub. It could be Kafka or Pulsar or RabbitMQ or any of the other message buses that are out there. And then it is sending, those events are being captured by the payment service, the inventory service. Then it's going to send back out a payment processed event. And then that goes out on the message bus. And then a notification service is looking for that payment processed event. It gets that, and it's going to send this. I missed one arrow. There should be an arrow coming back from the send confirmation back out to the user. The user may get an email. Your order has been placed. Instead of sitting there looking at a spinning, a spinning hourglass, they can do more shopping. This is great right? They can do some more shopping instead of sitting there waiting. Now you can actually, hey, why don't you do some more shopping while you wait for your order to be processed? So event-driven, asynchronous, highly asynchronous, okay? You can always tell if there's something asynchronous because you hear the word event, or there's a message bus in there somewhere, or there could be peer-to-peer message passing, which I think I have an example of that. This one uses an event broker or a message bus to handle that for you, but you'll see the word events and things like that. Those are more asynchronous types of things. I'm sending messages and events instead of a request response. Okay. Here's another pattern here. This one's an interesting pattern because one of the problems you get with event-driven things is if the payment fails, for example, how do I roll back all of that stuff that's already happened? I already pulled inventory, but now the payment failed. Now I've got to roll back. So Saga, the concept of Saga is it keeps track of those events that have been picked up and rolls them back. So it has the rollback events stored with it. So if any one of them fails, it will then trigger and then coordinate the rollback. So let's take a look at what this looks like. So we've got a Saga coordinator is what it's called. So when I first kick off, I place the order, I create a Saga, and the Saga is keeping track of the events that went out, the events that were handled, and then also if something fails, it knows how to back up those events. So there's a corollary rollback event for each event that goes out. This works really well if you've got really complex transactions that has several different microservices involved in fulfilling it, and there needs to be some kind of rollback mechanism. Okay. So it's much more complex, as you see, because now my Saga coordinator has to handle all those events. It increases the amount of events that are flowing between things. So I have to be mindful of that. I could do this in peer-to-peer, a Saga system, or I could use an event broker as well. I could use a message bus in there as well. I'm just not showing the message bus in this one. This is showing it as a peer-to-peer event-driven architecture. Okay. All right, another interesting aspect that we've already kind of talked about, a little bit touched on, is using tracing to give me observability and scalability. So if I get a bunch of events that comes in, like a sale went out and it's 50% off, and all of a sudden my website is getting clobbered, right? 1 million people are trying to log on to get this 50% off. I need to scale the number of order services I have out there and payment services, I need to scale those up as I'm seeing these events come through. Doing it after the fact is too late. So I need to observe what's going on and then dynamically create more instances of the same service. So something like this is, Kubernetes does actually a really good job with that. They've got an autoscaler built into Kubernetes where I can auto scale microservices, but I need some kind of tracing system so I can monitor the individual microservices and how many events they're processing per minute or per second, whatever the case may be, right? So in this case here, Jaeger is a tracing system. It is looking at the loads on each of the services, on the order service, the inventory, and the payment service, and it is going to scale them up or scale them back down depending on the loads that are working. This works very well. This is a common pattern that we see. This would be like a 4-tier type of design pattern or architecture that you're seeing. I got a monitoring and tracing layer. I've got an auto scaling or management layer of the service architecture. I've got a presentation layer and a data layer. So you can see the 4. People may even divide it into 5 different layers. Questions on observability and scaling?
Yes, I have a question. So is Jaeger more like it like analyzes like latency, and then Kubernetes is like more of an auto scaler? Is that a good way?
Yes. So Jaeger will feed its information into Kubernetes autoscaler and say, I need more, you've hit a threshold on your order service. Okay, I hit a threshold on my order service and it's really high, a really high threshold. I feed that information to Kubernetes autoscaler and it will scale more. It'll create more order services. So one is watching and the other one is doing. It's almost like bank robbers, right? You got the guy out front watching. He's out front, he's maybe walking the street. No one sees that he's a robber, but he may whistle or he may sound some kind of alarm for the guys inside saying, hey, the cops are coming. That's what Jaeger does, right? It's an alert system, really. But it's watching all the services saying, how are we doing? Oh, I need some more services. Let's tell Kubernetes, give me more, right? And then it goes back and keeps monitoring, right?
Yeah, that was good. Thank you. I like the analogy.
Okay, good. All right. Any other questions on observability and scaling? There's a temptation to throw the tracing and the observability into the autoscaler. Don't do it. Don't do it. That's really not that you've got separation of concerns there, and you also have a scaling problem as well. Because your Jaeger system, it's getting a lot of events. You want to make sure Kubernetes is doing something. It's a controller. It needs to be able to get its work done, right? Not listening to every single event that's coming in. Jaeger's really kind of just, hey, I'm monitoring things, and when I see a threshold, I'm going to alert the autoscaler. Okay. So microservices, they have to be loosely coupled. That's the goal. Do not put implicit coupling into your microservices. It will be awful to chase down. It will take hours and hours to figure out, or days to figure out, why is it doing this? Oh, because some microservice over here changed something and now you're completely hosed. That's tight coupling, okay? And a lot of times that's implicit, not written down anywhere. So it's very hard to do. Try and keep them as stateless as you possibly can. There are times where you want to use synchronous events or synchronous communications and asynchronous. You got to understand when to use one or the other. If you do need to block, you need to not do anything until you get a response back. That's synchronous, right? If you say, I absolutely need that order ID before I move forward, then use synchronous. Okay. Make sure that you have fault tolerance built in and security, that resilience, the fallback stuff. and then automate your CI/CD pipelines. Those are the things I would plead that you guys do. Okay. Any questions on this stuff? No questions?
I have kind of a specific question back when you were talking about single database per service. So how do unions normally happen in that case between different databases? The only way I really I've been exposed to kind of seeing it is something like the concept of annotation. I don't have a lot of context on what that is. And then a newer thing I've recently exposed to, but again I don't know much about, is an unmanaged model. Basically, those are the only two ways that I've kind of seen how to handle. But are there any other ways to handle communication between those databases and doing unions?
So this is where things get tricky. Your data model matters a lot, right?
Yeah.
If you're doing joins between two different databases that are across, that are like a MySQL database and two separate instances of those databases running, and you're doing a lot of joins across there, your data model's a mess.
Okay.
So you need to make sure that there's a whole course on data structures and data management. I don't know if Vanderbilt has one, but I had to take two of those courses for my PhD. And understanding third normal form and all the different forms on data architecture is extremely important. If you can decouple the data from each other and have as little reference between the two databases, you're far better off. If you're seeing a lot of joins between databases, they should be together in different tables, but then you probably can't move to a database per microservice. Now, it would just be the coordination and back end work you'd have to do would be too complex.
Okay, so I guess another kind of way, not how we deal with it, we're not exactly talking to a database, but we're getting references based on UUID. Let's say we wanted a specific piece of metadata for a piece of content. We send a request with the related UUID, and we basically get the response back. Is that the more appropriate way to handle it versus?
That would be a good way to handle it.
Okay.
Yeah.
All right.
That keeps your coupling a little bit further away, but yeah, try your best to make sure that your data lines up to your microservice boundaries as best you can.
Okay.
So let's talk about a little bit about that. In this simple architecture, I have an order service and a payment service and an inventory service, and they have different databases for each one. I'm not going to necessarily pass order information down to payment. I'm just going to say, can you give me this much money? You see what I'm saying? So instead of passing the whole order into the payment system, there's no reason to. I should only pass in, can you clear this much money? If the answer is yes, yeah. Oh, you cleared that much money? All right, I'm back on the order manager. Yep, you cleared that much money. Do I have inventory to do it? So all I'm passing in is, I need 5 red balls. Yes, you can have 5 red balls. They're mine. Boom. Okay. And I got the money, finish the order. In this case here, this simple example, the inventory knows nothing about orders. 0. It knows nothing. The payment system knows nothing about orders. It just knows that someone asked for, can this customer pay me $5? And the answer was yes. I take the money. The order has, yes, they got the money, and yes, I have the inventory. Then there's a fourth service called ship, right? Even the ship doesn't need to necessarily know the order. All it needs is what? The size of the box and the address. Maybe an order number to put on the shipping label. So when you start segmenting your data along those microservices, you can see I'm not replicating data, which is a dangerous thing a lot of times. right? So data architecture is a whole nother thing that we need, that I hate to say it, a lot of times people that deal in microservices, they punt on. They just say, their concept is, oh, data is available everywhere. Data is ubiquitous. The reality is that's not true, right? And it causes a lot of mess later on. So I hope I didn't confuse you completely, Hamza, with that.
No, we're kind of doing, we're not retrieving all the information from individual services. We're kind of doing a retrieve it along the way where we request the aggregates, which would be the value of the subsidy from the customer. And then from that value, that service that we've requested it from is also requesting it from the catalog, which contains all the information for our inventory, which is a course in this case.
That sounds like the right way to do it, to keep
Okay.
Yeah, it does.
Okay.
Okay.
Cool.
All right. What time are we at? 4:03. Okay, any other questions? I've got another 50 slides. I'm just kidding. We'll talk more next week. This stuff will most definitely be on the test. The things we're going to talk about next week are more, and I'll give you a, because we did run out of time. We always do. Next week, I'll give you a picture of what it looks like. It should be fun next week because we're going to talk about applying some of the things we've learned to different languages, like completable futures, multi-thread and task management in Java. You guys are used to this, right? We've done, composite, group threading and things like that. We're going to talk about multi-threading in Node.js, in Rust, and Go, Python as well. We'll go over composable threads in those as well. And there's comparison tables, all this stuff. This stuff will not be on the test, but this is for you guys for your careers. So when someone says, hey, you took this microservice architecture class and you learned Java, well, we don't use Java. And you go, well, that doesn't matter. I understand the concepts. And I noted in Node.js that, hey, to do lightweight threads, I can use event loops. And, you guys will have something in your back pocket that you can use for those interviews, and also that you can use to chat GPT and ask it questions to help you write the code that you need to get your work done. Okay, so we'll cover that next week, and then there's some follow-up things I want to talk to you guys about next week. Next week should be a load of fun. It's our last class. I will be in Japan next week on vacation, but I love you guys so much that, all right, it's going to be 7 in the morning. I'm going to be the only one awake, but that's fine. I'm an early riser, but I expect you guys to be there next week. Have fun, get ready. You got your exam next week, and then I will get your things graded before on Saturday before I head off to Japan. So your assignment 3, any feedback you get, you guys can hand in and you'll be done. So this class, all assignments, everything will be done by the 18th. And your grades I got to figure out how to put grades in to the official system. But those grades should be out the following week. So there you guys go. Any questions?
Oh, I hope you have a great vacation.